It's our pleasure to have the fourth and concluding lecture of Owen Gwilliam's universe.
Let's quickly recap what we did last time. The goal yesterday was that we formulated a version of deformation quantization and quantum moment maps. No longer for mechanics, but for field theories. Using this language of pre-factorization algebras. By moving from algebras to pre-factorization algebras, we could accommodate having an interesting space-time. So sort of ended on the following kind of picture. We had this category of opens the manifold M. It's all very tidy, but it's the wrong end. Just to make sure that everybody has the interpretation right, this M is supposed to be the space-time of the field theory. So we're doing Chern-Simons on a three manifold. This is the three manifold. And we're saying, I'm going to think about the quantum examples. So to each open set, a theory can associate a sort of chain complex over H bar. It's linear over H bar. And these are the operators in the QFT with their product structure. The product structure is organized by the pre-factorization structure. So I can talk about operators in U and U1 and U2, and then they multiply into something on U on V, say. So that's our playing the role of the observables. And then we had another kind of pre-factorization algebra associated to a Lie algebra G or an L infinity algebra. So physicists might call this a current algebra. Each element in G and region in spacetime has an associated kind of operator. And we're generating the algebra that those currents create. Okay. So these are sort of symmetries supported on submanifolds. Let's give some way of articulating that. And our version of a quantum moment map was that this pre-factorization algebra maps to this pre-factorization algebra. So each sort of abstract symmetry gives you some kind of operator in the actual field theory. So symmetries become observables, like we saw in the one. So this is a very nice articulation of, say, infinitesimal symmetries. And I asserted, without sort of demonstrating it by example, that for perturbative theories, this works very well. Sort of computations you see in the physics literature can be captured really sharply in this kind of way. So a lot of the formulas, for instance, that Pavel and Constantine are writing down, well, some versions of them fit in this story very nicely. So today I'd like to go back to thinking about group level symmetries. Hopefully touch on two sort of generalizations of group level symmetry, I should say. Touch on two things from physics, so there's something called higher form symmetries. Using the physics terminology are higher group symmetries. I find both of these terms, the vocabulary leaves a lot to be desired, but it's not my fault. This is due to the existence. So I want to explain what these are and how they get captured using pre-factorization algebras. And then if I have time, and I'm a little bit pessimistic that I'll have time, given how much I want to say. And I can connect these with an area of algebraic topology known as nonabelian Poincare duality. So if you're curious about this and I didn't get to it during the talk, come chat with me afterwards. This is the goal today. So like I said, I'm gonna talk about these higher level group symmetries, but I'm not going to explain really how they act on theories. I think doing that, if you look at the physics literature, there's tons of sort of assertions about how they're supposed to act. It would be a really sort of research project to take some of those and turn them into detailed mathematical treatments. Be delighted if anybody wanted to do that, so I'd be happy to talk. So, the higher form symmetries. Here's the setting. Again, we're going to have a manifold. So I'm going to start with an n-dimensional manifold. I'm going to pick P, which is the number, whole number between 0 and n. Okay. And B is a discrete group for the purposes of the talk today. Stir up mark. We'll see later that once I give a definition that depends on this information, P is bigger than 0, and D I need to be a. So it's fine.
Sorry, Owen, can I ask some slightly more general question?
Yeah.
About this outward. So, for example, are line operators meant to be captured by as observables? Because
Sure.
Okay, then what is this whole stratified story trying to capture? I mean, if you have defects already, or
So pre-factorization algebras can accommodate defects, and I'll give you an example in a few minutes. So that's sort of anticipating this issue. So pre-factorization algebras just assign things to regions. So to a region U, you would have the point defects, the line defects, the surface defects, whatever inside of there. Those should be observables that show up here. On the other hand, we think field theory should be in some sense local to global, right? The classical field theory certainly is. You're studying solutions to a PDE. So the measurements you can make in a region are sort of just depend on the behavior in that region. So you think the quantum thing should be as well. And so you need to figure out what's the appropriate way of reconstructing this functor, maybe on big, complicated open sets from the behavior on simpler open sets. So in the perturbative setting, we have a thing that just works. There's this Grothendieck topology due to Michael Weiss, and the observables in like perturbative theory satisfy codescent for that Grothendieck topology. But when you do non-perturbative things, like even something as simple as Dijkgraaf-Witten theory, it doesn't satisfy that. So the Weiss topology doesn't work anymore. So you might ask, is there some way of reconstructing the global information from sort of local information? One way of doing that is this blob homology of Morrison and Walker, or the beta factorization homology of Ayala and Francis and Rosenblum. So people have looked for a local to global principle. And you can imagine it's pretty complicated if you want to deal with an arbitrary and dimensional thing. So the thing I was going to talk about down here is a relatively lightweight local to global property that seems to be good enough exactly for these kinds of symmetries. Thanks.
So what's the last green word there?
That is abelian.
Sorry.
Okay. I get the complaints from my students, my undergraduate students. write in a hasty way. Okay. So suppose I fix this data. Let me give you the definition of a higher form symmetry that you would read in a physics paper. Form symmetry. They often write something like this to remind you of the input group and P of a theory on M consists of the following data. Pairs. Sigma a codimension E plus 1 submanifold of M. And G an element of the group T. Sorry. Each such pair a topological operator, which they like to write like this, on the theory. The theory. Such that if I take the same surface and label it by G, and I multiply it by G prime, same surface or really close by surface. Multiply the. Okay. I kid you not, this is basically what you see in the papers. The issue is, like, you need to, among other things, figure out what they mean by topological operator. This is left in some sense a little bit vague. Theory. And the way you multiply things if you have different submanifolds isn't specified in detail. They just give you some, draw some pictures and give you some examples, but there's no general rules. I think this is okay, right? People used to talk about symmetries before they knew about groups and group actions. Mathematicians had to come up with a definition that captured things more precisely. So here they're trying to define a P-form symmetry through the way it acts on a field theory. The operation is kind of like giving a representation. They're only specifying some of the elements of the algebra.
Oh, and I was surprised to what happens if you allow P equal to N there, so then you have a submanifold of codimension N plus 1. So yes, you have the empty set, but you want to talk about the empty set. Okay.
So we'd like to find a description that a mathematician can understand. I should say that although the definition is pretty hazy, if you look at the papers, they have tons of examples.
Yeah, with question. -1 is very important, right? Theta angle is -1 from
Okay. I'm sort of novel, like new to this, so I haven't thought about that case. So maybe, so you're saying, so theta angle is sort of on the whole manifold. So this, I see. So I should have started at
so
minus.
basically, yeah, adding topological terms to classical action is considered -1.
It's better. Okay, so that's a really good point. I find this choice of calling this a P-form symmetry often kind of confusing. There's always this one shifted thing that goes on. Great. Okay. But there's tons of examples and they show how they're really useful in field theory. So it's a slightly hazy notion with a lot of content. So putting some teeth into those things while we're doing a competition. Okay, so I don't quite know what this is, but if I take the case P equals 0, we've seen something that does this. seen a useful model for this. Namely this pre-factorization algebra we wrote the other day. So you remember that if I had some open set U, which was the tubular neighborhood of some codimension 1 manifold. So remember, if we had here's M, here's N, and you pick some little tubular neighborhood of it. This is U. And what we assigned to U here was D with its product structure. Essentially by displacing copies, by displacing N in the normal direction. Here, what I mean is you could think about U as a little annulus, and you concatenate annuli inside of each other. Sort of a product structure. You sort of can think about it as being supported on this. So that satisfies these conditions. Okay, for the case P equals 0, because we want a codimension 1 submanifold. Okay. But yesterday we actually saw that one of the nice things about this is that you could multiply opens that don't involve being neighborhoods of the same submanifold. Okay. So the nice thing about this example, this tells us how to multiply more complicated. So we could view this thing. I want to view this. So let's call this, so this would be what they might call D0, some model for D0 as an algebra object.
Would your D be what you call a UGN? Is that what you're saying?
This thing here is playing the role, yeah, like this UG. It's supposed to be a kind of symmetry. Oh, if I pick an element in G, so this, right, no, you're right. This is the collection. Okay, maybe better to call this is the UG of N, thank you, for G and D, which is of course as a set isomorphic to D. Okay. Thank you. I had one more comment I meant to make on my notes, which is that pi naught of compact supported maps from U to BD. There's another way of writing that might psychologically make it less full, which is that maps into BD have to do with cohomology of U with coefficients in D. But I'm taking compactly supported, so we could just view this as studying compactly supported homology with coefficients in D. That puts it in a world that feels less like. Okay. So we've seen that pre-factorization algebras, at the very least of this type, they capture zero form symmetries. Now let's just think about P being bigger. About P greater than 0. Okay, so now I need to tell you some facts from algebraic topology. So remember, call it BD was this Eilenberg-MacLane space. For P greater than 0 and D abelian. Can you read this bubble?
Yes, yeah.
So I'm going to quit calling it D. To emphasize it's abelian, I'm going to call it A now. We have an abelian group A. But B of P plus one at A, that's gonna be another space. Be defined to be this Eilenberg-MacLane space, Ka P plus one. A space with the property.
Let's probably BP of A is Ka equals 1. Right? So for P equals 0, I should have BA equals Ka1. So that something's off with the shifts.
GA equals.
So there's BP minus 1 and KAP plus 1, but I think the difference between shifts should be.
No. The same number.
Sorry. Sorry. No, it's great.
I K of this space of homotopy groups. Well, they're A equals P plus 1, and there's 0 else. So just like in this case, there's a homotopy group just in this particular degree. And so, as an example, model of B2Z is given by CP. Actually, does anybody know another convenient example for something bigger than 1? Like I think a space you know?
Oh, it's like coming is in a yarn space.
What is that?
Don't think so, since the homotopy group is of S, we have higher homotopy.
Yeah. I just don't know any other examples where there's a easy to describe group and an easy to describe space.
I mean, you can sort of get symmetric powers or something.
And I mean, I feel almost symmetric powers, right?
Yeah.
Okay. Great. Okay, so in parallel with the stuff about the classifying space, there's this really neat fact, which is that it has a moduli interpretation. So if I take some space Y and I look at all its continuous maps into P plus 1 of A, and I take the connected components of that space, that is the P plus first cohomology of Y with coefficients in A. So it represents higher cohomology. This is why Eilenberg and MacLane introduced it. And if you're this kind of person, you could also think about it as a moduli space of higher A germs. We won't use that. So another cool fact, or just assert, view it as a group. As if you set up, there's a functor B if you're careful enough, and B of P plus 1 of A is B applied to B of P of A. You can do this iterative process. So A started out being an abelian group, you just keep applying B and it's still an abelian group. It's some sort of higher abelian group. Let's do something very simple here. So to capture consider refactorization. Well, there's this composite, which is compactly supported maps into B plus 1 of A. And then you could take pi out again if you wanted. End up in sets. And this composite, as we mentioned earlier, you can think about as the functor, which is compactly supported P plus 1 cohomology conditions. Now, the analysis we did in the P equals 0 case carries over. So the let's just kind of do it. Suppose I take sigma codimension P plus 1 submanifold. Okay. And suppose the way Grisha's concerns from last time, the tubular neighborhood of sigma, so let's call it U, of sigma is homeomorphic or diffeomorphic to sigma cross R with P plus 1. So I've got this submanifold, and I want to know if I thicken it up a little bit, it really just looks like crossing with RP plus 1. In general, it'll be some kind of vector bundle, the normal bundle. But that can be somewhat twisted. So I just want to keep things really simple here. Okay, so let's think about that special case. Then compactly supported maps from U to BP plus 1 of A. Well, I can view U as this product, right? So I can think about it as a map from sigma cross RP plus 1. I'm also assuming this is closed. This is just from some map from sigma and compactly supported maps from R to P plus 1 into BP plus 1 of A. Okay. We saw last time that this thing is the same thing as pointed maps from SP plus 1 to BP plus 1 A. This is actually equivalent to A. So I'm just giving you some facts from algebraic topology. So this whole thing is isomorphic to the set A. If you just run through the topology, I mean, more or less. So that means we can again use this picture as was suggested. Each on sigma, I get to pick an element from A. That's what this thing does. So I have the U sub G of sigma for each of them. And you can analyze the product structure. You can think about displacing sigma a little bit to multiply. I guess we could draw even the two pictures. In this case, sigma is a point. I label it by some element little a. I displace it a little bit over here. I put A prime. So, they're really living in some little disks. And then I can include in a slightly bigger disk. And the output is A plus A prime. It has to be abelian because you can move this disk around. So the Ekman-Hilbert argument is why.
Then the picture suggests that there's a bit more than that and that there's like an E P plus 1 algebra. Yeah.
Yes. Once you stop sticking these Eilenberg plane spaces, you get much more distance. Yeah, I mean, keeping track of not picking I naught is the thing. It's harder to deal with this than this, but I just want to make it probably to show you get that. So this thing captures everything they ask for here, and it tells you how to multiply things with different shapes as long as they don't overlap. Okay, so we just saw why it needs to be abelian too by the Ekman-Hilbert argument. Questions? Yeah.
It's going along with that last question. Do physicists actually think about the case when you take A to be some iterated loop space rather than just a abelian group, or is that mostly a mathematical interest?
They do. That's where these higher group symmetries come. So there's a way of reading some of the history of theoretical physics over the last 40 years or something, which is that periodically some physicist learns a little more algebraic topology and figures out some way to interpret it in physics that's sort of rich and meaningful. And then there's this. So recently they learned about Postnikov systems. That's what we're going to talk about. I mean, it goes the other way too. Like we learn things from them and change that we. I've been talking kind of abstractly. I want to gesture right now about towards an example of a symmetry in an actual field, but this is gonna be kind of rough. So they just forewarn. So I want to give you an example for one of symmetry. So A will be Z mod 2, which everyone knows is Sergey's favorite group. So we're going to be thinking in this case, because I'm doing a one-form symmetry, we're going to be thinking about, if you'd like, compactly supported homology, degree 2, coefficients in Z2. So is this one-form symmetry group. That's what we're aiming for, and I want to say how it acts on something. So the sort of thing I have in mind is T is an SU2 gauge theory. So, example, if you think about Yang Mills or transits. So the thing that's going to really matter for what we're talking about is that the field content of the theory includes running over SU2 bundle, principal SU2 bundles, P over your manifold. Okay. So how, just schematically, how is SU2 going to relate to Z mod 2? The thing to notice is that the center of SU2 is plus or minus the identity. Okay, which is of course isomorphic. So Z mod 2 is showing up as the center of SU2. We could replace 2 by n and we get a Z mod n. Okay. So let me now say something kind of schematic. Suppose I had alpha in H2 compactly supported of M. I want to describe how this is going to act on the theory. So one way of thinking about this thing is as a check 2 cycle. So viewpoint 1, view as a check 2 cocycle for some cover then. You can use that information because Z mod 2, of course, now sits in the SU2. You can use it to modify the cocycle equation to write down an SU2. So twist the cocycle condition. Check 1 cocycle condition for an SU2. So you're sort of making something that's kind of like an SU2 bundle. Locally, it looks like an SU2 bundle, but globally it's not because you twisted the cocycle conditions. In that sense, it's supposed to be acting on the theory. You should be able to deal with these twists. Whatever it means to have the theory, you should be able to talk about that sort of situation. Now, there's another way of thinking about this. Viewpoint 2. So H2 of C. It's the same thing as Hn minus 2, and with coefficients in Z mod 2. Okay. So view alpha as a codimension 2 submanifold. We could hope that there's some representative cocycle. So codimension 2 submanifold sigma labeled by elements of Z mod, or maybe some formal linear combination. Okay. So we could think about it as a check cocycle, or in this picture as sort of a labeled submanifold, which is this P-form picture. Okay, so this is an example of a understanding the papers, right? This is an example of a Hooft defect. Okay. Vague gesture in the direction of physics kind of makes sense. Okay. I should also say this particular symmetry is called center symmetry. So you can see there's lots of names. Or sometimes an electric one form symmetry. So lots of names because this idea got run into in many different ways, right? Hooft effect, electric one form symmetry, center symmetry. Kind of reflect about some of these different pictures, like the check picture.
Sorry, what do you mean by twist? The one cocycle.
I have UI, UJ, UK. To write down the SU2 bundle, I pick an element of your smoothie varying maybe function. Sorry, a function from here, each overlap, SU2. And if you go around 3 times on this section, you get the identity, right?
Yeah.
So I'm just saying instead has to equal alpha on the triple overlap.
So we should get some twisted bundle.
Yeah, it's not an SU2 bundle.
Uh,
It's an SU2. It looks like an SU2 bundle, except it jumps across these submanifolds. Like the gluing them together sort of gets a disorder operative jumps in this kind of discrete way.
So maybe I need a question then. So because I thought the symmetry would act kind of in space of fields, but then you're saying that the action does not act in space of field because it leaves this space of fields. Because it's no, you're taking answer to your bundle.
Yes, you have to enlarge your notion of the field constant to allow these things as well. Yeah, I would say that that's one way of reading what they're saying. They might have said you thought Yang-Mills meant you just worked with SU2 bundles, but you don't. In principle, you're allowed to do this thing to modify it, and whatever it means to do Yang-Mills, you should also be able to talk about to the path integral over these kinds of things.
So you're saying that one way to interpret when they say defects is these jumps in the local cocycle.
These are examples of defects.
Yeah.
These are examples of like disorder operators. I mean, that sounds really weird and abstract, but like we see it like all the time in nature, right? Like if you are building a silicon wafer, right? There's like silicon and then there's like air or vacuum or something, right? So like the physics changes in some abrupt way at a boundary. Other questions? These are all great questions. Okay, so that was higher form symmetry. I now want to describe higher group symmetry. I'm going to be a little bit schematic here. Maybe thought of it as like whetting your appetite for homotopy theory. Okay. So if I know how to do some things with groups, one natural thing to ask is I can make bigger groups by extending groups. So if I knew what to do with the group D and D prime, I could ask, so I'm making a group that sort of assembles that information in this sort of short exact sequence, right? It kind of looks like you have D and D prime in some sort of like twisted product involving those two elements. Okay. But we know that something similar happens in spaces in the notion of a fiber. So and similarly, about extensions of these higher groups. So I can imagine I have B of D, I don't know, B2 of A. I could ask for some sort of fiber bundle over BD, whose fiber is this sort of principal bundle for this higher group. Okay. Now this data, sort of like principal bundle. Okay. This data is classified, giving a principal bundle is classified by picking a map. So in this case, you add 1 to it. And over it, there's some universal. Of this. Okay, so such extensions are classified by maps. Like this. So there's this thing people call a K-invariant. That's supposed to be an E upper 3. Just sort of you're doing that, maybe a better way to write it would be like this. E B2 of A. It's like that. You know, there's EG, BG. Okay. That's a pullback, right? That's a pullback, yeah. So.
And they are different groups.
Yeah, A and D are different groups. Yeah. Yeah, so this is the 3 group homology of D with coefficient. You like these? So let's just suppose that you can kind of extend higher groups like this. And if we think about this, we think about compact exported maps into Y, we might view it as combining a 0 form symmetry for D, the 1 form symmetry to A. So it binds together 0 form symmetry for D with the 1 form symmetry for A. Right? Each of these spaces separately had some higher form symmetry. So this is an example of what they call a higher group symmetry. So there's an example, which I'd like to understand, but I haven't gone through, but I read in a paper. I just want to mention. So Yang mills for the group SUN. The 1 form symmetry. Yeah, its center. C mod n. You saw the n equals 2 case over here. That should be a big N. And a 0 form symmetry. We did charge conjugation. There's a Z mod 2 there. And they're actually twisted together in some interesting way. So together they assemble into exactly this kind of picture, a 0, 1 symmetry. Where the Z mod 2 acts on the center. The paper says this by flipping the Dinkin diagram. I don't know what that means in concrete terms, but that's a puzzle maybe to figure out as a mathematician.
So what paper is this?
There's this really nice lecture series by hard watch. They were the lecture, and then there were a bunch of other speakers. If you look up lectures on generalized symmetries, maybe last summer. It's a very nice little lecture.
Do you have any interpretation for the K invariant here?
What does interpretation mean?
For the K invariant, because
I think about the K invariant as classifying the extension as a higher group.
for the specific example, so this, because you have these two layers, but then they would interact somehow, they would be invariant.
Yeah, I agree. There should be some kind of, there's some. We saw the center symmetry was related to these defects, for these codimension two surface defects or codimension two defects. So there's some kind of higher category there. And there's some. There should be some higher categorical interpretation. No?
So this is the uncertain driver.
Yeah, so somehow, yeah, these kind of tricks get used lots of places. So Lorenzo and Schreiber use it for some set of purposes. People in theoretical physics are using it for other purposes. Yeah. And it's just some statement about the way spaces work. So let me just finish this last comment about we connect to this comment. So this kind of extension picture is part of the theory of Poincare systems or towers. So this is an idea in algebraic topology. The idea of building up a space by slowly turning on its homotopy groups. Okay, so you start with the space. Here's an example of a tower. You start with the space, I'll call it X1. And it's B of some group pi1. Okay, so it only has a homotopy group in pi. The next stage of the tower, pick up vibration x2 over x1. Where the fiber, so yeah, a fiber looks like B2 of some group I2. So there's going to be a list of groups. I1, I2, I3. Okay. This can be non-abelian, but all of these will be abelian. Okay. X1 only has one interesting homotopy group, and it's exactly pi1. Now X2 has two homotopy groups. This has a pi1, X2 being pi1, pi2 of X2 being pi2. Okay, all the other ones are 0. So it's just in 2 layers. And this is classified, of course, by a map I'll call K2 into B3. Okay, so I have some list.
A little nervous about that since you might have a non-trivial action of pi1 and pi2. I don't think you can.
Yeah, I probably should. Okay. What's the right way to say it?
Complicated. I don't remember the right way of saying that. Let's just assume that the action is trivial.
Let's assume it's trivial. Now I want to make an X3 by turning on something in pi3. That's going to be given by a K3. The B for pi3. So I'm supposed to have a list of K indents. Okay. So what you're doing is it's this kind of layered cake philosophy. You're building a space by pi1, pi2, pi3, and how they fit together. Okay. So up to this subtlety, the kind of amazing thing is, if I said what's happening at the bottom right correctly, in fact, every space is homotopy equivalent Okay? Every path connected space is weakly equivalent. So from the point of view of homotopy theory, it's the same. So the limit, inverse limit of xn's as you let n go to infinity. Using with, the group ik here being ik of x. So you have to work out what the k invariants are that go with x, but there exists some such that you can view x as built up stage by stage from this group theoretic information.
What's written below the K2?
So I'm sort of thinking about a very special situation where pi 1 x in a kind of moving way. So you need to take more.
Coefficients in the local system.
Yeah, yeah, it's just the appropriate version. Okay. So this is all well documented in books going back to like the 1940s or something. It's not sort of on my brainstem and I'm not sure how to say it. The idea is you can think about a homotopy type as built from this kind of group theoretic information. And what I want to say, almost done here. So the upshot is this. There was nothing about our analysis of the pre-factorization algebras that didn't let us stick in any pointed space as the target. So any pointed, let's say connected space X determines a pre-factorization algebra by thinking about compact supported maps into X, which is a functor from open N. Okay. Krasnikov theory tells us it is, according to the higher group's symmetry, X. You can think about what we're assembling is the zero form symmetry for pi 1, the 1 form symmetry for pi 2, the 2 form symmetry for pi 3, and so on and so forth. Okay. So if you want the analysis of higher group symmetries, these kind of discrete higher group symmetries in physics, boils down to understanding Postnikov systems and seeing how it interacts with this compact coordinate maps to that space. Okay, so that's sort of an assertion, and I think there's a lot of interesting things to do there. In particular, seeing it concretely manifested in physics examples and maybe non-physics examples. So I have 5 minutes left. I'm going to talk about the nonabelian Poincare duality for 5 minutes. Maybe I should remark over here. You can generalize, we're ending up in top because X is a topological space. If you work in some more sophisticated setting, like the theory of derived differential geometry, you can pick X to be some kind of derived stack there, talk about compact supported maps into that. This gets changed, it becomes derived stacks, but you get a very lovely picture of sort of smooth generalized global symmetries. Okay. And I should say that just sounds very abstract, but if you did the holomorphic version of this, on Riemann surfaces, that is more or less how Bailen and Drinfeld construct the Bailen and Drinfeld grass model, which is like a key object in geometric length theory. I just want to gesture at that because there's some obvious generalizations you should be aware of. Okay. So we've been thinking about compactly supported maps into it's P plus P of A. We're thinking about this as some version of compact supported equal modular coefficients. We just sort of said, okay, I can replace this by some space X, and I view this sort of some version of nonabelian X valued compactly supported cohomology. So you might ask, well, I can usually compute homology using, say, like Eilenberg-Steenrod axioms, right? Or cover or whatever. There's some way of doing that. So can I also compute this? So let me tell you. Lost the following theorem. This is due to Paolo Salvatore, Jacob Lurie, and there's several other proofs. The following statement. So I want to compute compactly supported maps from M into X. Now, I might try to cover M by disks, or think about knowing how these things, this functor behaves on disks, n-dimensional disks. So, n-dimensional. So what I could think about is maps from K tuples of Rn into X, and I take the colimit. So if I think about K different disks inside of my manifold M, I could take the colimit over all embedded, K-fold embeddings. Okay, so there's some sort of diagram here. So every single one of these, of course, extends to this. So this colimit over all these ways of thinking about disks inside of M also has to map to here. There's a canonical map. This is a weak equivalence if X is n-1 connected. Which means the homotypic groups I k of X equals 0, K. Okay. So this should be kind of plausible because compactly supported maps from Rn into X is the n-fold base loops of X. It just doesn't know anything about the lower homotopy groups of X. So there's no way you could reconstruct that information. But this says that so long as you know about this space and the way it multiplies, its En structure, then you can fully reconstruct this. Yeah.
Yeah, this entire series, I guess I may have missed something, but compactly supported maps, how does that always end up like on Rn that you're viewing that as always giving some sort of loop space or, you know, in loop space, as opposed to just being compact like on a disk, you know, something not with the bounds?
Because it's an open disk.
Yeah.
So close to the boundary, it all has to go to the base of the bolts. So you can extend it canonically to a map on Sn.
Okay.
Where you stick the point at infinity up there.
So
it's a base map effect from Sn.
okay, because we're talking about maps on open disks, so we have to get the compactly supported, we have to compactify Rn with the 1 point.
Gotcha. Okay. So you can see that we have this pre-factorization algebra, and it reconstructs the global data we want under this hypothesis on the target. So the way you prove this, you can reinterpret this as saying it's a kind of Cauchy for a certain topology. Maybe work in progress says that work in progress is that there are growth-peak topologies that allow you to weaken this hypothesis. And so it doesn't have to be totally connected, it could be n minus k connected. And now you reconstruct, not by knowing the value on disks, but on neighborhoods of k-dimensional k-dimensional complexes, cell complexes inside of the thing. So this is like a k-dimensional, if I have a point, its tubular neighborhood is a little ball. If I had a graph inside of my manifold, I take a tubular neighborhood, I could do n minus 2 connected, because you're actually getting a kind of path in space time information. So that's the main takeaway is that this theorem admits a refinement, and it suggests what the appropriate local to global property is for generalized global symmetries, and hence possibly for non-perturbative field theory. Okay, I've gone over time. I apologize. Thank you very much. More questions?
So where is the Poincare duality?
You do ordinary Poincare duality, you stick an x being this case. And if m is compact, you take this kind of target, you know that compact supported cohomology and cohomology are the same. There's a nice discussion of this in Laurie's higher algebra book. That's probably the best place to look.
So you're saying that that theorem is a generalization of the usual Poincare.
By allowing nonabelian coefficients. So the way Jacob proves it is that he actually, this is not the only way to prove it. The way he proves it is he uses ordinary Poincare duality and then kind of leverages it to get the nonabelian case. But you can directly prove the nonabelian case and deduce the abelian case.
Well, I guess if there are no more questions, let's thank Owen for his beautiful lecture. Resume in 25 minutes.